It's crazy, right? Our phones are basically bottomless pits of music, photos, videos. Huge HD movies just pop up on our screens in like a second. It's practically digital magic. You know what I mean? Like, you got a 3-minute song that used to take up so much space, and now you can share it in a flash. So if you've ever wondered how they pull that off, well, you've come to the right place.
That's exactly what we're diving into today. You, our amazing listener, you sent us some seriously cool stuff, especially Angelina Dominguez's AP CSP 221 data compression video. It's from Code Curious, by the way. So what we're aiming to do in this deep dive is unpack the whole data compression thing, really break it down. We'll look at the different techniques and figure out when each approach is, the best tool for the job.
Exactly. Because at the end of the day, it's all about being smart with our digital stuff. It's about finding a smoother, more efficient way to store all that information, whether it's your favorite song, vacation pics, or even just plain text. And it all comes down to using fewer bits. When we talk about bits, think of those as the tiny on-off switches that make up all our digital data. Data compression is like finding the shortest, most elegant way to flip those switches. That saves you storage space, makes things faster when you're sending files online, and you know what? It can actually save you money too.
Absolutely. Let's kick things off with a fundamental question. Why do we even care about data compression in the first place? You touched on it, but let's really dig into the reasons behind its importance. The big one that always comes up is storage. Yeah, sure, our devices in the cloud seem to have more and more space these days, but it's like our hunger for digital content is growing even faster.
It's true. We're always making and consuming more data, so figuring out how to shrink those files down is a big deal. Like, you get a new phone, tons of storage, you feel like you're on top of the world, and then bam, out of nowhere, a year later, you're getting those storage full warnings.
Yeah, exactly. No matter how much storage we have, there's always a limit. Compression helps us keep that digital clutter under control. And then, of course, there's network bandwidth. Ever tried streaming a high-def video on a slow connection? Ugh, the buffering, the lag, it's the worst.
I know, it's so frustrating.
Compressing files before we send them across the internet, or even just our home Wi-Fi, it makes things so much faster. Smaller files equal less data to move around, which means faster downloads, smoother streaming, and just a happier network overall.
And let's not forget the money part.
Yeah.
Compressing data can actually help us save some cash. Angelina mentioned that in her video too. Like, if a company needs less physical space on their servers to store the same info, that's a big win for their hardware budget.
Yeah, and when they're sending less data back and forth, that can mean lower internet bills too.
It all adds up, right? Especially for those giant data centers, the ones with petabytes of data. Even shrinking those files by 20% could save them millions on hardware and energy costs. That's huge. So it's clear that being efficient is a big reason why these compression technologies are so important.
It is. So how do we actually pull off this shrinking magic? What's the secret sauce of data compression? Well, it all comes down to finding redundancy in the data. Think about it like this. If you've got a sentence that repeats the same word over and over again, instead of writing the whole word every time, why not use a shortcut? Like a symbol or a code.
Okay, I get it. So like Angelina showed in her video, let's say we've got the sequence XXXOOXX. Instead of writing it all out, we could just say X302X2.
Right. Exactly. Now, you're right. For a tiny string like that, the difference isn't huge.
Yeah, it doesn't seem like a big deal.
But as Angelina explained, the bigger the file, the more chances we have to spot those repeated patterns and get rid of that redundancy. That's where the real savings kick in.
Right. It makes sense. And it's not just about counting those repetitions, right? Text compression can be even smarter. Angelina had that example where she got rid of some characters and used symbols instead. The original text was 28 bytes, and she managed to squeeze it down to 15 bytes. That's like a 46% reduction. It's pretty impressive.
It is, and that showcases another key technique, substitution. We're talking about finding those characters or groups of characters that pop up all the time and replacing them with something shorter. Her Humpty Dumpty example really brought this home. She had this block of compressed text next to a key, what we often call a dictionary.
Oh yeah, I remember that. For our listener, if you haven't seen the video, imagine a jumble of letters and weird symbols. And then this separate list that tells you what each one means, like a decoder ring or something. Angelina even challenged us to try and figure it out ourselves. It was fun trying to crack the code. So we've got the basic idea down, but are there different types of tricks within lossless and lossy compression? I mean, are there specific algorithms that make this happen? Like, I've heard of things like Huffman coding or Lempel-Ziv. Those sound like pretty clever ways for computers to find those repeating patterns and represent them efficiently, especially for lossless compression, right?
Exactly, and the Humpty Dumpty example, the results are pretty cool. The original text was 142 bytes, and the compressed version ended up being just 80 bytes. But here's the catch, and Angelina made this really clear. You also have to send that key or dictionary along with the compressed data. Otherwise, how's the other person going to decode it? In this case, the dictionary added another 31 bytes.
So it's not just about the compressed text itself. We have to factor in the dictionary too.
Yep. So when you add it all up, the total package was 111 bytes. Still, that's a 21% reduction, which is nothing to sneeze at. And it really highlights a key thing about lossless compression. You need that complete recipe to get back to the original data perfectly. That's how those huge text files we see online can travel so fast. It's all thanks to those clever recipes. So that was lossless compression. We've seen it in action with the text examples. Can you remind us what makes lossless compression special? What's its defining feature?
Totally. Lossless compression, it's like a magic trick where nothing really disappears. When you decompress the file, you get back exactly what you started with. Every single bit, no information lost in the process. It's all about spotting those patterns and creating that recipe, like that dictionary, to rebuild the original perfectly.
Exactly right. Angelina used this great analogy. Imagine a picture of a tiny island with a huge blue sky in the background.
Okay, I can picture it.
Now, in that image, you've got massive areas where the pixels are all the same color. So instead of storing that color info for each pixel, lossless compression can just say, hey, this whole section is this exact shade of blue and it repeats this many times.
So it's like saying blue, blue, blue 1,000 times versus just saying blue by 1,000. I get it.
Right. And because the computer knows the dimensions of the picture, it can recreate that big blue area perfectly. No need to spell out each individual pixel. That makes sense for simple areas of color. But what about a super detailed photo with lots of patterns and variations? Does lossless compression still work well for those?
Yeah, I'm curious about that too.
That's a great question. Lossless methods will definitely still find those redundancies. But the compression ratios, how much smaller the file gets, they might not be as dramatic for complex pictures compared to something with lots of solid color. But the key is, we're not sacrificing any information. And that's why lossless compression is so crucial for certain types of files. Think about those programs on your computer, the executable files. If even one tiny bit gets messed up during compression or decompression, the whole program could crash.
Yeah, that'd be bad.
Same goes for text documents, spreadsheets, databases, anything where getting the data right is super important. Losing even a single character or number could really mess things up. There are all sorts of lossless compression formats out there. You've probably used ZIP files, right? Those are great for archiving stuff.
Yeah, ZIP files, I use those all the time. So that's lossless, perfect recovery, no data lost. Now, let's flip the script and talk about lossy compression. Name kind of gives it away. Something's getting lost here. Sounds a bit risky.
It does, and in a way, that's exactly what's happening. Lossy compression throws away some of the data for good. Once you've compressed a file this way and then decompressed it, you can't get back to the original, not perfectly. Some info is gone forever.
Okay, hold on. Why would we ever want to throw away data? It seems counterintuitive.
The main reason is to get those files way smaller than we usually can with lossless compression. The thinking is, the data we're tossing out, it's either redundant in a different way, not that important for how we experience it, or maybe we can't even perceive it with our senses. Angelina gave this cool example with audio files. There are sounds that exist outside of what humans can normally hear, so algorithms like those used for MP3s, they can find and remove those frequencies. The file gets much smaller, and most of us wouldn't notice any difference in how it sounds. Think about streaming music. It's almost always in a lossy format like MP3.
Right, to save on data.
Exactly. It's like getting rid of sounds we can't even hear anyway. But Angelina also warned us about using lossy compression on text. Like, if you started removing vowels randomly, like she showed, words like food or fed would become total gibberish.
Yeah, that's a recipe for disaster.
For sure. Lossy compression for text is a no-go. But when we're talking about images, audio, and video, it's super useful. Take pictures, for example, and the JPEG format. Angelina explained how the JPEG algorithm, it's a lossy method, and it works by dividing images into small blocks.
Okay, I remember that. And within those blocks, if the colors are pretty similar, the algorithm can just use one average color for the whole block, right? Instead of storing all those subtle shades of blue in the sky, it just says, this whole area is this one shade of blue.
You got it. And that simplification shrinks the file. But if you zoom in really close on a JPEG that's been compressed a lot, you might start seeing some blockiness or a blurriness. It's not a perfect copy of the original. Think about those funny cat pictures everyone shares online. Those are almost always JPEGs. Maybe we lose a tiny bit of detail, but it's worth it to share them quickly and save space.
So it's a trade-off. We sacrifice a little bit of quality, usually not even noticeable, to get a much smaller file that's easier to store and share. Angelina mentioned that platforms like cloud storage services, they love these smaller, lossy, compressed images because they save a ton of space and bandwidth.
Absolutely. For most things we do with images, audio, and video, this trade-off makes sense. We get much smaller files, and the quality loss is barely there if we even notice it at all. Think about streaming video. Without lossy compression, those files would take forever to load and eat up tons of data. You've probably heard of MP3 for audio and JPEG for images, right? Those are common lossy formats.
Yeah, I know those. So how do we decide which type of compression to use? It seems like it depends on what kind of data we're dealing with and what we're trying to achieve.
Right. If quality is king, and we absolutely need to get back to the original data perfectly, like with software programs, important documents, anything where accuracy is key, then lossless compression is the only way to go. We need that guarantee that nothing's changed.
Got it.
Right.
But if we're all about getting the smallest file possible, fast transfer speeds, and we're okay with a little quality reduction, then lossy compression is the better choice.
Exactly. It's all about finding that balance. And as Angelina said, even when we're using lossy compression, it doesn't mean we're losing information in a way that really affects us. Lossless keeps every bit safe and sound, while lossy cleverly removes data that's often redundant or beyond what we can perceive. The result, smaller files without sacrificing the experience.
Okay, let's do a quick review of what we've learned in this deep dive. We started by defining data compression, the art of shrinking down digital information. Then we talk about why it's so important, saving space, speeding up transfers, and even saving money. We looked at the basic idea of how it all works, finding that redundancy in data, like repeating characters and using techniques like substitution.
And we took a deep dive into the two main types of compression. Lossless, which keeps everything intact, and lossy, which throws away some data to get smaller files. We also talked about when to use each type, lossless for critical data where accuracy matters most, and lossy for media where a little quality loss is usually okay.
So our awesome listener, now that you know how they shrink down all that digital stuff, think about all the behind-the-scenes magic that happens every time you stream a video, listen to music, or download a file. What other cool tricks are they using to make our online world so smooth and fast? It makes you appreciate all the technology working in the background, doesn't it?